Let's do just one more example. Let's again solve this system of linear equations if we can. Okay, so let's write it in augmented matrix notation. First row is the coefficients of my first equation. So 1, -3, 2, 5, -17. And the second row are the coefficients of my second equation. 2, 0, 4, -3, 22. Okay. We need to put this in reduced row echelon form. Or let's start with row echelon form. Let's get it into row echelon form. That will tell us what we're dealing with. So I have a leading term right here. It's already 1. That's beautiful. I love it. I want a 0 below it. So I'm going to take -2 times row 1. I'm going to add it to row 2. That's my new row 2. That way I could get this to be a 0. So I leave row 1 as is. Row 2 becomes -2 plus 2 is 0. As intended, I wanted that to be a 0. That's why I'm doing this particular operation. -2 times 3 is 6, plus 0 is 6. -2 times 2 is -4, plus 4 is 0. And -2 times 5 is -10, plus -3 is -13. And finally, -2 times -17 is positive 34. 34 plus 22 is 56. Okay. And already we're in row echelon form. We've got that stair-step pattern. Okay. So looking at this, we definitely have at least one solution. We don't have any of those nonsense equations or nonsense rows that tell us we have no solution. So we definitely have at least one solution. We have 2 leading entries, 2 meaningful equations, but we have 4 variables. So we will have infinitely many solutions. Okay. We want to characterize those solutions. All right. So taking a look at this, we could do back substitution. For infinitely many solutions, I think it's a pain. I think it's much easier to do reduced row echelon form. So I'm just going to jump to getting us to reduced row echelon form. Okay. So I need this to be a 0. I've got a leading entry here. I need to turn that leading entry into 1, and I need all the entries above it to be 0. That's what I need to do to get into reduced row echelon form. So to do that, I'm going to first multiply row 2 by positive 1/2 and add it to row 1, and that will be my new row 1. Okay, so I have 0 plus 1 is 1. 1/2 times 6 is 3, plus -3 is 0. That 0 is the whole reason I'm doing this operation, so it's good that I got it. 1/2 times 0 plus 2 is 2. 1/2 times -13 is -13 halves. Plus 5. 5 is 10 halves. So I'm going to get -3 halves. And then 1/2 times 56 is 28. Plus -17 is 11. Okay. And while we're at it, let's get a leading coefficient of 1 here. Let's change that into a 1 by taking 1/6 times row 2 and making that my new row 2. So I get 0, 1, 0, negative 13/6, and 56/6, which reduces to 28/3. Okay, this is now in reduced row echelon form. Notice, by the way, and I probably should have mentioned this earlier once we were in row echelon form right here. We have 2 leading entries. We have 4 variables. So that means we'll not have just 1, but we'll have 2 free variables because we have 2 columns that do not have a leading entry. The columns without a leading entry should be your free variables. We have 2 columns without a leading entry, so we're going to have 2 free variables. Okay, and we could also see that here when we're in reduced row echelon form, but you could see that as soon as you get to row echelon form. So my equations are 1x plus 0y plus, let's see, 1x1. I think we're using x1, x2, x3, x4. So 1x1 plus 0x2 plus 2x3 minus 3 halves x4 equals 11. And the second equation is 1x2 plus 0x3 minus 13/6 x4 equals 28/3. Okay? Now, we can easily solve for x1. We could get x1 by itself by just subtracting this to the other side, moving this to the other side. And so I can express x1 in terms of x3 and x4. Same for x2. If I move this to the other side, I can easily express x2 in terms of x4. And that's why we choose for x3 and x4 to be our free variables. We will always have 2 free variables, but technically I could choose almost any of the variables I want to be the free variables. But generally, it's going to be easiest if you choose your columns without leading entries to be the variables that are free variables. Okay, so I am going to choose, let's choose x3 to be s and x4 to be t. And when I say free variables, that means we are free to choose whatever we want for those variables. They could be anything, and then we define the other variables in terms of the free variables. Okay, but the free variables could be anything. You could choose them to be whatever you want. Okay, so you could choose s to be whatever you want. You could choose t to be whatever you want, and we will have a solution to this system. So if I plug in and solve for x1, I have x1 equals negative 2x3, which is s, plus 3 halves x4, which is t, plus 11. And x2 is going to be, move the x4 over, that's 13/6, and x4 is t, so 13/6 t plus 28/3. Okay, so I have x1 and x2 in terms of my free variables s and t. So if I'm free to choose s and t to be whatever I want. I could choose s to be 17, I could choose t to be 1043. But then x1 and x2 have to follow this pattern for whatever s and t you choose. Okay? So let's write our solution in vector form. x1, x2, x3, x4. And so x1 Let's go ahead and break this up. We could already kind of see what's going on here. So let's have the coefficients of s. For x1, that's -2. For x2, there is no s term, so I have 0 s's. For x3, I have 1 s. And for x4, x4 is equal to t, so there are no s's for x4. Okay? Plus t times the vector of coefficients for t. So for x1, that's 3/2. For x2, that's 13/6. For x3, there are no t's in x3, so that's 0. And for x4, that's 1. And then finally, my vector of constant values. So for x1, I have a constant 11. For x2, I have a constant that's 28/3. And x3 and x4 don't have any constants, so 0 and 0. And so that's my solution. I have 2 free variables in 4 dimensions. We haven't talked about that, but if we have 2 free variables in 4 dimensions, this is actually a plane that lives in 4-dimensional space. Okay? It's a 2-dimensional object that lives in 4-dimensional space. And just to be clear, notice this is the same as what we have, right? -2s, so x1 is -2s plus 3/2 t plus 11. Okay, -2s plus 3/2 t plus 11. And that's true for all of these. I'm just writing them in vector form.